Guys, I'm going to be talking about lenses today and the results from our practical. So lenses. Well, lenses are used in a variety of ways to studying the universe. What they are is they're materials which bend light, and they're used in telescopes to help us see. But how does a lens work? Well, a light ray from our light box is what we saw in our practical. Light ray will be emitted from our light box. It will travel in a parallel fashion, meaning they won't intersect. The light rays will then move into the convex lens, and because the convex lens is more dense than the air surrounding it, the light rays will bend or refract. When they refract or bend, they'll reach what's called a focal point. All the light rays will move in here, converging until this point here, known as the focal point. The distance between the midsection of the lens, or halfway through the converging lens, and the point where the light rays meet, that's called the focal length. In this diagram, the focal length is known as 20 mils, and the object is 40 mils behind the lens. I'm now going to talk to you and show you the results we got from our prac. So we had 3 different measurements from your practical, and these are the measurements I'd like you to use. So please use these measurements in your answers. What we have here is the light box in black in all 3 diagrams. The light box is in the same position, it's at the beginning of the graph paper. There's a 30 centimeter ruler with the millimeters over here, here, and here. We'll start with this one here. The object, or the light box, is placed 60 mils from the lens. At this point, the light begins to hit the lens, it will converge, and this will be the focal point here, where the light rays meet. The focal length is the distance between halfway from the lens until the focal point, and that's 70 mils. Again, the distance from the light box to the lens is 60 mils, and the distance from halfway through the lens into the focal point is 70 mils. Over here, the object is now closer to the lens, it's 40 mils between the light box and the lens. Again, the focal length is the same. Just like over here, the focal length is the same, and now the distance between the lens and the light box is larger. So what we can see here is that the focal point is where all the light rays converge, and the focal length will remain the same in all 3 diagrams. This is because the way that the light is bent, it's the same degree that it is bent, so it will meet at the same point. From this practice, the results that you need to be taking from it, or have an understanding of, is that as you move the lens closer, so from this diagram we started out at 60 mils, this is our image, the size of the image. Look at the light rays, how spread apart they are. If you move to 40 mils, so the lens is now 40 mils from the light box, look how large and far apart the light rays are. This is where we're forming our image here. So clearly the image is larger when we move the lens closer to the object, as opposed to moving it further away. Just like over here, if we move the lens further away, the image is now smaller. So the key results are the focal length will remain the same as you change the distance between the object and the lens, and the image will get larger as you move the lens closer, and it will get smaller as you move over here as you move the lens further away. This is showing exactly the same results with the simulation. As you move the object closer to the lens, as in this diagram here, this was the initial diagram, over here you moved it closer, let's move there, the object is now, sorry, the image over here is now larger in size, and it's the other way around. It's the other way around because the light rays have gone over here to the top light ray, and now it's become the bottom light ray. Just like this bottom light ray has now become the top light ray. Again, if you move the object over here to the light box, it's moved further away from where it began, over here, you now have a smaller image. It's exactly the same as what we're having in the practical, and this is the ideas I want you to be able to understand. Thanks for watching. In your practical, you need to be drawing the image of an object 30 mils behind the lens, 70 mils with the focal length, again 80 mils behind the lens, and 40 mils behind the lens with 30 mil focal point. You also need to do one with the concave lens. Using these images here, which was in the presentation I just showed you, you answer the questions. What do you notice about the size of the object as it moves closer to the convex lens, further away from the convex lens, and How can a lens be used to magnify light? How does it make the image larger or smaller depending on where it is? These simulations will help with the first two questions, and the video here as a link will also help with the third question. Conclusion is just to summarize your results. I hope this helps.